Okay, so think about this for a second. How does something move through a space that's, well, fundamentally broken? Today, we're jumping headfirst into the wild world of fractals and a totally new kind of math that helps us make sense of their infinite complexity.
Let's kick things off with a little puzzle. You know, we all kind of get how a drop of ink spreads out in a glass of water, right? Or how heat moves down a metal rod. It's smooth, it's continuous, but what if it wasn't? What if the path it had to travel on was just shattered into an infinite number of tiny pieces with huge gaps in between?
Well, this is exactly the kind of broken path we're talking about. It's called a Cantor set, and right away it throws up a huge problem. I mean, how can anything move across something that's mostly just gaps, empty space? A regular math, the stuff we all learned in school, it just completely falls apart here.
So, okay, how in the world do you even build one of these things? You'd think it's got to be incredibly complicated, but the recipe is, well, it's actually surprisingly simple.
All right, here's how it works. You start with just a solid line, step 1. Step 2, you chop out the middle third. Gone. Now you're left with 2 smaller lines on either side, right? And you just do it again. Take the middle third out of those 2 lines, and then you do it again to the 4 lines you have left. And again, forever.
And this is where things get really, really weird. It creates this total paradox, because if you think about it, you've removed the middle third, then a third of what's left, and so on. If you add it all up, you've actually removed the entire length of the original line. The total length of what's left is 0. But, and this is the crazy part, there are still an infinite number of points left behind. So, how do you measure that? What even is that?
Clearly, we need a new kind of ruler. Our old ideas of length, width, and height just don't apply. So mathematicians came up with something called fractal dimension. It's not about how long something is, it's about its complexity. It's a measure of how good it is at filling up space, even when it's full of holes.
So what does that mean for our Cantor set? Well, it's not 1D like a line, and it's not 0D like a single point. It's somewhere in between. It has a fractal dimension of about 0.63. Think about that. It's more than just a collection of disconnected dots, but it's definitely less than a solid continuous line. And that fractional dimension, that's a huge red flag for our standard math. Classic calculus with derivatives, integrals, all that good stuff. It loves smooth, continuous curves. It's built for that world, but you show it something like this, a fragmented, broken set, it just throws its hands up and breaks. So, to solve our puzzle, we're going to need a completely new kind of calculus.
And believe it or not, scientists have built one. It's called CZ calculus. Think of it as a custom-built toolkit, designed from the ground up for one specific tough job: to do math on functions that only exist on those scattered leftover points of a fractal.
Now, this is the really clever part. At the heart of this new calculus is a brilliant trick. You see our broken Cantor set, and next to it, you see this thing that looks like a staircase. That's the staircase function, and it's basically a mathematical magic trick. It acts like a bridge. It scoops up all those scattered points from the fractal, ignores all the empty gaps, and lines them all up neatly into one continuous path. And suddenly, we have something our old calculus tools can actually work with. Yeah, the researchers who developed this stuff say it themselves. This staircase function is the absolute key. It's the whole shebang. It's the one thing that lets us connect the weird, broken world of fractals to the smooth, continuous world of calculus that we already know how to use. Okay, so we've got our new toolkit, the CZ calculus, and its secret weapon, the staircase function. Now we can finally go back to that original question. How does something actually move or diffuse across one of these broken paths?
And this is where the model gets really interesting. It doesn't just stop at making space a fractal. It asks a wild question: what if time itself is also fractal? I know, it's a bit of a head-scratcher. But we can now model a particle moving through a fractal space, we'll call its complexity zeta, and also moving through a chunky fractal timeline with its own complexity, which we'll call beta.
And the amazing thing is, this model predicts 3 totally different kinds of movement. It all depends on how the complexity of the space compares to the complexity of time. If the path in space is simpler than the path in time, the particle actually spreads faster than normal. That's superdiffusion. But if the space is more complex and gnarly than time, the particle gets bogged down, it gets trapped, and it spreads way, way slower. That's subdiffusion. And here it is. This is the payoff, right here on this graph. You can see all 3 scenarios playing out. Look at that red line shooting upwards. That's your superdiffusion, spreading like wildfire.
The blue line is just your standard normal diffusion. But then look at the green line. It's barely moving. That's subdiffusion. That particle is just getting completely stuck in the intricate broken maze of the fractal path.
So look, this is obviously some really fascinating math. But you might be thinking, okay, that's cool, but what's the point? Why should I care about this outside of a university? Well, here's the thing. Fractals aren't just some abstract idea. They are everywhere. The antenna in your cell phone, it's probably a fractal. The way a tumor grows, fractal. The branching network of blood vessels in your own body, that's a fractal too. Even the texture of your bones can be analyzed this way to check for things like osteoporosis.
So what this new calculus gives us is a powerful new lens. It's a way to understand and predict what's happening in all these incredibly complex, fragmented systems, the very systems where our old math just gave up. It's about finding the hidden order in things that, on the surface, just look like a total mess. We're learning to see that what looks like chaos might actually be an incredibly intricate pattern just waiting to be understood.
And that really leaves you with a big final thought, doesn't it? What other complex patterns out there in the world, things that seem totally random and chaotic, are just sitting there, waiting for us to invent the right kind of math to finally understand them?